Okay. So the next question that we are going to solve is the sole question that we provide in exercise set 12. After all, the last modules of this course are very short. Therefore, the statistical procedures that we practice are almost similar to each other, and one application here is sufficient. We have already performed one application in our theoretical lecture. Now, in recitation, we are just going to strengthen our knowledge on the estimation of absolute performance metrics. Now, if you remember from our 7th model, we have performed a queuing simulation for an MM1 queue. Remember, MM1 queues are the simplest of the queuing systems, for which we already have a closed form performance metric calculated with a closed form solution. There is no necessity to run a simulation of such a system because of these closed form formulations. However, we have done it for what? To increase the reliability of the simulation technique in the eyes of the class participants. Okay, so we have seen that if you run a very, very longer application where the warm-up periods statistics are excluded in the outputs, the results of a simulation of an MM1Q system are very consistent with the results that you obtain through the closed form formulations of the performance metrics. So we have basically simulated the MM1 single server queue system for this purpose, okay? Now, here we are going to perform an output analysis for this system, and it says that we have run a simulation of 8 replications, and obviously these are 8 independent replications. I mean, there is no necessity to indicate that. If replications are not going to independent, why I am performing these replications, right? So we have run a simulation of 8 independent replications of this system, and the time spent in the queue by each client in each replication is present in Q1 tab of the ES12 Excel file. Now, let me show that Excel file to you, which is available in the learning management system as well. So we have run the MM1Q system for a sufficiently large number of clients here, but I mean for a limited amount of time, of course. Most probably in that question, the question was asking us to run the simulation of the MM1Q system from 9 a.m. to 4 p.m. for 7 hours only. And during these 7 hours in independent replications, the number of clients that you may observe can be different. As you can see, in some of the replications, you observe a number of clients which is 167, which means in a total of 7 hours, only 167 clients are they have been served. But in an extreme case, in one of the replications, which is the 7th replication here, we could have served to 173 clients in that example. Now, remember, MM1Q has inter-arrival times, which are independently and exponentially distributed, and the service times are independently and exponentially distributed with another rate parameter. Therefore, we should not expect to have a stable queue profile, stable size of the queue during the simulation or during the observation of such a queuing system, because exponential distribution is not very stable because of its high tails. Unlikely if it was the normal distribution, if the inter-arrival times and the service times were to be distributed normally, in that case, there wouldn't be so much variance in the number of customers that have been served in a 7 hours long periods. They could have been much more consistent from replication to replication, because normal distribution have lower tails. We do not observe so extreme cases in normal distribution. Now, these are what? Let me go back to the question. These are what? These are the time spent in the queue by each client, okay? Now, if you check the first column here, for some clients, the time that they spend in the queue is simply 0, but for some of them it is positive, okay? So in each replication here, there are so many 0 values in our sample, right? because most of the customers in such a queuing system may have waited only 0 minutes in the queue, which means they simply, when they arrive, they find the server idle. But in some cases, please check, for a large number of consecutive customers, there's a certain positive queue waiting times. And that's the problem, my friends. You see, within a replication, the time spent in the queue by consecutive customers are definitely dependent on each other. So you see, when we observe a 0, we observe many other zeros after that. When we observe a very, very large value, let me show that to you, very large value, we observe a few more large queue waiting times after that as well. Another example is here. For example, in this replication, here, the 111 customer has waited 8 minutes in the queue. And after that, how many more customers waited for a positive amount of time in the queue? Please check. 43 consecutive customers have waited a positive amount of time in the queue because of this instability created by this customer. Most probably, the queue waiting times were long. Now, why I am indicating this? Within a replication, the queue waiting times are not independent, my friends. For consecutive clients, the queue waiting times are definitely dependent on each other. Therefore, by simply taking the average of these values and calculating the sample variance of these, we cannot provide us with a confidence interval. Okay, we need to introduce independency between results, my friends. Okay, here you see, here in this cell, I am calculating the average waiting time for the first replication. And in the next cell, I am calculating the average waiting time for the second replication. Now, I should change this to 173, but it does not make any difference in the results, my friends. Even if you take the empty cells here, in the empty cells, if the values are not 0, they are not going to be introduced in the average in Excel. But what you can do is simply exclude them, which will not make any difference. So here's the thing. For every replication, I calculate the within replication averages. Okay. And in each replication, I calculate the, I can calculate the within sample, replication sample variances, which I'm not going to do. Okay. So there is no basically practical purpose of calculating the variance of these 168 values. Why? Because with that sample variance, I can never ever develop a confidence interval. Because if I want to develop a confidence interval, definitely there should be independence between the observations in a sample, though here we do not have any independence. The consecutive values are definitely dependent on each other. Therefore, by using a single short replication, I cannot provide the user with a confidence interval, my friends. So what I'm going to do is this. I am going to perform replications, okay? So there are 8 replications here. In each replication, we are using a different random number sequence. Therefore, the outputs of the replications are definitely independent from each other. The averages within replication averages are definitely independent from each other. Now, for these 8 values, for these 8 averages, I can also calculate a sample variance. And just like I have done in the previous example in the validation procedure, I can use the t-distribution to develop a confidence interval. Now, these 8 values are having a sample variance equal to 7.49, my friends. Okay. Now, how do we calculate it? Let me go back to the solution. Now, these 8 replication averages are here. There are 8 replication averages here. The first index here indicates that this average belongs to the first replication. Okay. This average belongs to third replication. And the second index is given in dot notation, which means we have taken this average. So if there is a dot here, then this means this statistic is an average, which is taking over the second index, whereas the second index represents the clients in that replication. Okay, so this is the client's average waiting time in the queue. Now, I am also calculating the between replication or across replication averages. And for these 8 values, 8 within replication averages, their average is equal to 4.94 approximately. Okay, so simply this is the average of averages. Okay, average of averages. So the inner average is the replication average, the outer average is the across replication average. And this is my performance metric that I obtain after 8 replications. Okay. Now we assume that this is an unbiased estimate for the expected time spent in the queue, because after all, this is a terminating simulation that we perform here. Therefore, the initial conditions must definitely be provided to the simulation model. We have the bias problem in steady state simulations. However, this simulation is only 7 hours long, and there is a certain initial and terminal condition for the system that we need to provide the model with. Okay, so we need to calculate the sample variance for these 8 outputs because we want to provide a confidence interval for the true expected waiting time in the queue. Now, this sample variance is automatically calculated by var.s function in Excel. But how do we perform it? Please check. First, we subtract this average from each of these within replication averages and calculate the deviations and square them. These are called the squared deviations. And finally, we sum them up. We sum up the squared deviations. Again, we divide it to the number of replications minus 1. Again, with the same reason, because we are using a lie that we obtained from our replications to calculate another lie. Okay, we need to penalize ourselves with 1 degrees of freedom here in order to get, obviously, I mean, we are penalizing ourselves, but the main reason that we do it is what? In order to get an unbiased variance estimation. Okay, if you divide it to 1 over, if you divide this sum of squared deviations to m, you would definitely get a biased variance. Now, the unbiased variance estimation is 7.49, and the sample standard deviation here is 2.73. Now we need to provide a confidence interval while using the sample standard deviation. We want to provide this 95% confidence interval for the expected waiting time in the queue. Okay, so the sample standard deviation should be divided to the number of replications in square root, which is square root of 8. And we need to multiply it with the certain t quantile if we want to provide us with a 0.95% confidence interval. Then from both sides of the t distribution, we need to split 0.025 probability. And for that probability and degrees of freedom 7, for that probability and degrees of freedom 7, we can check the t table. And degrees of freedom 7, the t quantile we need to take is 2.37, as you can see. For 2.37 here, we can build our confidence interval as 2.65 and 7.23. So what we can say here is this. With respect to our simulation results of 8 independent replications, the true expected waiting time in the queue for these clients is somewhere between 2.65 and 7.23 with a 95% confidence level. Okay, so it is not, I mean, we cannot say that with 95% probability it is in this interval. We cannot say this, but we can only say this with 95% confidence level, the true expected waiting time in the queue is in this interval. We can say now this interval, my friends, is not very narrow. Okay, I mean, with 8 replications, the confidence interval that we get is not giving us a solid information, accurate information. Unfortunately, we definitely would like to reduce the width of that confidence interval. At this point, the half width of this confidence interval, which is calculated by this component, as you can see, the half width of this confidence interval is 2.29. Okay, we would like to reduce this half width as much as we can to get a certain accuracy. Now, let me show that these Sample variance is calculated automatically by the variance.s formula in Excel, but you can also calculate the sample variance by calculating the deviations from the mean, then squaring them and summing them up and dividing it to m-1, which is 7 in this case. And the sample standard deviation is the square root of it. The standard error is the sample standard deviation divided by the square root of the number of replications, which is basically this part. This is the standard error. So this component is called the standard error. And when you multiply it with the t quantile, which is obtained by the inverse CDF of the t distribution at 0.975 quantile probability, 0.975 cumulative probability with 7 degrees of freedom, you can calculate the t quantile without looking at the t table by using Excel, and the half width is obtained in a similar fashion here. So we are performing a manual calculation here to calculate the half width. Here we are using Excel, and the 95% confidence intervals upper bound and lower bound are automatically calculated here by introducing everything that we have calculated with direct formulations, and we have consistent results in Excel and also in our manual solution here. Now let's go back to our question. In the part C, it says that in part A, it has said that calculate an estimate for expected time spent in the queue. And that estimate, my friends, was simply the average of these 8 replication averages. So the average across replications is the estimate for the expected waiting time in the queue. Now, secondly, we have built a 95% confidence interval for the expected time spent in the queue. Now, the question asks us to provide a 90% prediction interval for the average time spent in the queue on any day. So I have already mentioned about this in the lecture, in the theoretical lecture. So a confidence interval tries to bound the expected waiting time in the system, whereas a prediction interval tries to bound the average waiting time on any day. Okay, because we know that even if expected waiting time is a solid constant value, the average waiting time we observe from day to day can be different, because even in the original system, not a day is a very similar one to another day. Okay, so we need to calculate a, please be careful, 90% prediction interval. Okay, not 95, 90% prediction interval. So this means we need to check another quantile from the t distribution, t table. And let's go back to the solution here. Now, the difference between the confidence interval and the prediction interval is that when we are calculating the square of the standard error, we need to multiply it not just with 1 over m, but we also add 1 to that multiplier. So the formulation is updated as, again, by using a t quantile, this time with a 0.05 probability on the right-hand side. We multiply the standard deviation not with square root of 1 over n, but square root of 1 plus 1 over m, because we need to introduce the inherent standard deviation in the prediction by this one. Okay. Now, please note that if you increase the number of replications so much, you will definitely get a more accurate result for the expected, for the statistics, for the estimation of the expected queue time, because as the number of replications increases, that standard error will converge to 0. However, that component will never converge to 0. There will always be inherent standard deviation caused by the differences from day to day of the original system. Therefore, prediction intervals will always be wider than the confidence interval. Now, when you apply this formulation, again, you use the sample standard deviation as 2.74 approximately, but this time you are multiplying it with the square root of 1 plus 1 over 8, and you use another t quantile, this time obtained for a 0.05 tail probability for 0.05 tail probability, and with the same degrees of freedom, the T quantile that you need to use is 1.89 approximately. And the prediction interval here is 0.056 to 10.44. Now, that does not make any sense, right? I mean, you say that the daily average number of daily average waiting time in the queue is going to predict to, with a 95% confidence level, is predicted to be between a negative value and a positive value here. I mean, we know that the average waiting time can never be negative, okay? So this lower bound here does not make any sense. We definitely know that the theoretical lower bound is 0 because no waiting time can be less than 0. I mean, why do we get such a result? First thing is that the MM1Q is not very stable, okay? So calculating a prediction interval for an MM1Q is not very sensible because it's not very stable, but we can calculate a confidence interval for that. Now, if you increase the number of replications, this confidence interval's width is going to converge to 0. Okay, if you have performed sufficiently large number of replications, this approximately 4.5, the width of this confidence interval is approximately 4.5. And it is just going to diminish if you increase the number of replications, which means this prediction interval is also going to get narrower. And if it gets narrow, obviously the lower bound is going to increase above 0, and the prediction interval will make much more sense. Okay. So this is just a practical question, and with a limited number of replications, such as 8 here, my friends, unfortunately, you should not rely on the confidence interval that you calculate or the prediction interval that you calculate. This is just for practical purposes. In this question, we are working with a small number of values to calculate the sample variance or the sample standard deviation easily. And obviously, let me tell you this, during the exam, you will even get a smaller number of replications in your calculations, okay? Even 8 observations in a sample is very large to calculate the sample variance in a small amount of time by hand. I mean, even when I'm doing here, solving my question, I am showing you the Excel results, and I am not explicitly showing how this sample variance is calculated because it certainly takes some time to do each operation by hand, one by one. Therefore, I mean, you can be assured that in the exams, most probably you are going to perform this procedure if we ask such a question. And when you perform this procedure, you will definitely get a even smaller number of replications here, not 8, but 6 or 5, and even 4. Okay, but as I have told you, such a small number of replications does not make any sense. We definitely need to increase the number of replications to get a narrower confidence interval and even narrower prediction interval here. Now, the essence of this question is not ending here. Before giving a break, I need to complete the course question. So here it says, if we desire to reduce the 95% half-width to 0.5, how many more replications do we need to run? Now, at this point, you need to consider that these 8 replications that we have performed are simply what? Pilot study. Okay, it's a pilot study. They are pilot replications. Okay, so we are not going to provide the user with this confidence interval. We will definitely increase the number of replications after performing these 8 replications. But why we have done this? For a pilot study, because we have seen that if we perform 8 replications, we are going to get such a large half-width, which is approximately 2.29. But the user tells us to get a half-width for the confidence interval, which is no larger than 0.5. Okay, so it expects to get a 95% half-width, which is no larger than 0.5. But if user gets such a half-width, this means the width of the confidence interval will be at most 1. Okay, which is going to be more accurate to make a comment on the results of the expected waiting time in the queue. Okay, so how we can reduce the length of the confidence interval, how we can reduce the half-width to 0.5 by definitely increasing the number of replications. But the question here is this: I do not want to increase my number of replications more than necessary. Okay, so I'm expecting this. I mean, give me a solid number of replications that I need to perform additional to this pilot study so that I will get a half-width which is no larger than 0.5. So I do not want to, I mean, you know, I have a strong computer and I can increase the number of replications as much as I want, as long as I turn off the animation in Arena. And I can definitely get fast results here. But here we are trying to keep it to a limited number of replications. What we get as a half-width, if it becomes 0.5, that is just going to be sufficient for us. Now, how do we perform it? Now, I have already explained the theoretical background of this in the theoretical class. So we are basically using this formulation, my friends, okay? So if I want to reduce my half-width to 0.5, then I can use the sample standard deviation estimate that I get from my pilot replications. Now, for 8 replications, the sample standard deviation across replication results was 2.74 approximately. And I multiply that value with 0.975 quantile of the Z distribution, which is the standard normal distribution, my friends. I have already explained why I'm not using the T distribution here, because T distribution requires the degrees of freedom parameter, and the degrees of freedom parameter is also dependent on the number of replications. Now here I want to determine the number of replications by taking this value to the left-hand side and everything on the right-hand side. But if I use a T quantile here, that M value will never be taken to the left-hand side. Therefore, I am replacing it with this standard normal quantile. And there is no danger of doing that, because what we know from the percentage points of the students' T distribution here, as the degrees of freedom parameter increases, the quantiles of the T distribution, they converge to the quantiles of the standard normal distribution. So after all, our objective here is to increase the number of replications, right? And we expect that as we increase the number of replications, the T quantile that we are going to get is going, the T quantile that we are supposed to write here in this formulation is going to converge to the standard normal quantile. So there is no danger of replacing it with a Z quantile here. And we divide this multiplication to the desired half-width size. So the user expects a half-width of a 0.5 length. We write it as in the denominator here. And this ratio will be squared to provide us with a lower bound for the number of replications. So this value, my friends, when all values are replaced, is telling us the number of replications that you need to perform in order to get a half-width of 0.5, in order to get such an accurate confidence interval. The number of replications that you need to perform is definitely to be greater than or equal to 115.11. Obviously, we are going to choose an integer results because the number of replications can only be integers. So this means the number of replications should be at least 116. We already have performed, please check, we already have performed 8 replications. Now, if the number of replications is supposed to be 116, then we need 108 more replications here to get a half-width which is as small as as large as 0.5, okay? Sorry, as small as 0.5, okay? Now, let's go back to the last part of the question, then we are going to give a break. If we desire to reduce the 99% half-width to 5% of the expected time spent in the queue, how many more replications do we need to run? Now, actually, this part of the question is no different than part D. but what is different? Okay, it is different, but not so different. First of all, this time we do want the desired half width for a 99% confidence interval. Okay, and we want this 99% half width to be less than, not to be less than a certain value like this, but we want it to be less than the 5% of the expected time spent in the queue. Okay, less than the 5% of the expected time spent in the queue. So how do we perform it? I mean, only there's a few basic steps that we need to perform. Please check. Please check. Here, the indication is this. This is the half-width formulation, right? The half-width is calculated by multiplying the t quantile with the theoretical standard deviation across replications divided by the square root of the number of replications. This is the half-width formula that we have collected from the theoretical lecture, okay? And we want this to be no larger than 5% of the estimate that we want to get. Okay, 5% of the estimate that we want to get. Now, we neither know the standard deviation across replications, because in order to know this theoretical standard deviation, we definitely need what? We need to run an infinite many number of replications. And we never know this true theta value. This is the expected time spent in the queue, unfortunately. We can only calculate statistical estimates for this sigma and for this theta. And what we have done previously is basically this, okay? So we have said that y bar 1.94 here is an estimation for this theta, and this 2.74 is a statistical estimation for sigma. Now, please check, my friends. Again, I'm going to perform the same operations that I have done in the lecture, theoretical lecture. In this inequality, what I want to identify is the number of replications that I need to perform. So I am just going to collect everything to the right-hand side and keep this square root of m to the left-hand side, and this inequality will turn into this form. So I'm just going to take this 0.05 theta in the denominator, and t quantile will be multiplied with sigma and divided by this 5% of the statistical estimate. I'm sorry, expected time spent in the queue. And I will square this, and I will say that m should be definitely greater than or equal to this. Now, what are the problems here? First of all, if I do not know m, how can I calculate the t quantile with m1 minus degrees of freedom? So I replace this t quantile again with the z quantile, or the quantile of normal distribution. Since this time we are trying to focus on a 99% confidence interval, then the z quantile that I need to check from the standard normal table should be 0.995. Okay. Now, let me show that to you. For statistical tables, the CDF table of the standard normal distribution for 0.995, my friends, which is somewhere between in these two values. The Z quantile is 2.57 or 58, somewhere between these two values. So it should be 0.575, okay? So the T quantile that I have is 0.575 or 176. I mean, this result is obtained from Excel. Excel always tells you the truth. Now, another danger here is what? I really do not know the theoretical standard deviation across replications and the expected waiting time. So what I can do for these values, I can simply replace them with the statistical estimates that I collected from my first 8 replications. So in the first 8 replications, I have estimated the expected waiting time in the queue as 4.94 and the standard deviation across replications as 2.74. So I'm just going to replace these two unknown values with the statistical estimates that I collected from my pilot study for 8 replications. And now I have all values that I need, and the square of these values is approximately 813.64. Now, m definitely should be greater than or equal to this, and this means the least number of replications that I require in order to get a certain accuracy relative accuracy with respect to the estimate that I want to get with 99% confidence level, I definitely need to run 840 replications. It says I have already performed 8 replications. This means only 860 more replications have remained. Okay. So these two parts, D and E here, are very important, especially, my friends, for your last homework. So please, if you have not understand at this point, you are free to ask any questions once I turn off the recording.